Ethylene is fed into direct and oxychlorination reactors. In direct chlorination, ethylene is fed alongside chlorine to the bubble chlorine reactor R201, which at 100 degrees C and 2 bar with an iron chloride catalyst reacts to form EDC. A small amount of oxygen is added to the chlorine to help inhibit side reactions. EDC from the reactor is sent to EDC purification. In oxychlorination, ethylene, oxygen, and HCl, recycled from downstream, are fed into the fluid bed reactor R101, operating at 305 degrees C and 5 bar with a copper chloride catalyst to produce EDC in water. The product stream passes into a quench column, where an alkaline solution neutralizes excess HCl. The product passes to an azeotropic drying column to remove water. EDC from the reactors and low purity EDC from downstream are mixed and sent to column C301, containing 47 stages at 1.2 bar to remove light hydrocarbons. The bottom products pass to a second column C302, containing 6 stages at 1.2 bar, removing heavy hydrocarbon byproducts like trichloroethane. EDC is distillate. High purity EDC is fed into the pyrolysis reactor R401 at 550 degrees C and 16.5 bar, decomposing into VCM and HCl. The product stream contains almost equal VCM, EDC and HCl, as reactor conversion is approximately 50%. It passes through a flash to remove heavy byproducts, before passing to a VCM purification. The heavy waste stream passes to a flash to recover EDC and is recycled to the purification section. Crude VCM enters column C501, containing 42 stages at 11 bar, where HCl is recovered in the distillate and sent back to oxychlorination. VCM and EDC pass to C502, containing 30 stages at 5 bar. Pure EDC leaves the bottom of the column and is recycled back to pyrolysis, while pure VCM leaves in the distillate for sale.
The thermodynamic model is chosen based on the operating conditions and components in each process unit. The main chemicals involved, water, VCM, EDC and HCl, are polar and form non-ideal mixtures, while operating pressures range between 1.2 and 16.5 bar. Hence, the non-random two-liquid model coupled with the Redlich-Kwong model is chosen as it accurately describes highly non-ideal systems up to pressures of approximately 10 atmospheres. The most relevant alternative global model is the universal quasi-chemical model coupled with Redlich-Kwong, which has a similar modelling capability as NRTL-RK. With literature validation of NRTL-RK to experimental data, the use of UniQuack-RK is not justified. The 3 main reactors are simulated using RStoich, which simulates based on manually inputted reactions and their conversions. It is used whenever reaction kinetics are unavailable. In this case, using RStoich is advantageous because chemical reactions and conversions are available from literature and side reactions can be included selectively. RStoich is able to automatically calculate reaction enthalpy or heat duty of reactors based on operating conditions and the reacting species. It is assumed the effect of operating conditions on reaction kinetics are the same as cited literature. Distillation columns in the process are simulating using DSTWU. The split fraction of the specified light and heavy keys are cited from literature and inputted along with the reflux ratio or number of stages. DSTWU then utilises the Wynne-Underwood-Gillen shortcut method to calculate distillation column specifications like feed state location, distillation and bottom flow rates, heat duties and pressure drop. This data is used for more rigorous simulation using RadFrac. However, with confirmation from literature values, DSTWU proves to be more suitable.
Within energy analysis, heaters and coolers were added to the original Aspen simulation in places where the stream's temperatures required a significant change. Aspen then generated the heat duty for these heaters, coolers, reboilers and condensers of the distillation columns. For the method of choosing what is a significant amount of energy, we have decided that heat duty greater than 10 megawatts should be considered. From the table, the direct oxychlorination and pyrolysis reactors, as well as the first EDC and VCM distillation columns, show significant heat duties. For the heat integration process, however, the reactors were not included, as that would be too complicated for the Aspen simulation. Heat integration was done by using a pinch analysis to reduce the overall heating and cooling utilities. The heat exchanger network here shows the feasible matches that were formed. The reboilers and condensers were included, but this was difficult to model on Aspen. Therefore, only the streams were used in the implementation of the heat integration on the Aspen simulation. These are the feasible matches that were implemented into Aspen. When incorporating the heat exchangers into Aspen, a countercurrent heat exchanger was chosen, as this has the highest efficiency. The heat integration strategy implemented into the Aspen simulation resulted in only a 4% energy saving in the heating utility and 8% in the cooling utility. This is not a large energy saving. Most of the integration proposed included the reboiler and condenser, which had significant heat fluxes. Nonetheless, it is a significant amount being saved, which would have otherwise been provided by producing steam using natural gas.